Hello everyone, let's solve a problem from GATE 2019, question number 34 from Aerospace Engineering paper. The question is, the envisaged incompressible flow field resulting from a uniform laminar flow past a circular cylinder of radius r centered at the origin is given by these velocity components. Okay, so we have a cylinder, so uniform flow of velocity u is flowing past this cylinder which is having radius of capital R. Okay, so then the velocity components in cylindrical coordinates will be defined by this two equations. So ur is given by capital U 1 minus capital R square by small r square cos theta, and u theta is equal to minus u into 1 plus capital R square minus small r square sin theta, where u r in u theta are the radial and azimuthal velocity components in polar coordinates as shown in the figure. So u is the free stream speed, and ignore the effects of gravity. The azimuthal location in the first quadrant on the cylinder at which the pressure coefficient is 0 is dash. Okay, so first what we have to do is to find the pressure coefficient, right? So the pressure coefficient is allocated on the surface of the cylinder, right? So first we will find the velocity components on the surface of the cylinder and then substitute them in the coefficient of pressure to find the coefficient of pressure, and you will equate that to 0 to find the angle at which it becomes 0, right? Let's go and solve this. Since we have been given this, since we are going to find the location on the surface of the cylinder, let's find the velocity components on the surface of the cylinder, which will be given by, on the surface of the cylinder radius would become capital R, right? So u into 1 minus r square by r square cos theta, which will be 0, right? Our radial component of velocity, it becomes 0 here, and the azimuthal component of velocity will have some value. So by substituting small r is equal to capital R, so we will have sin theta. So then this becomes r square will get cancelled. So then we will get minus 2u sin theta as our azimuthal component of velocity, right? Now we know that the coefficient of pressure is given by 1 minus u by capital U. So this u is given by the total velocity, that is given by u theta square plus ur square. Okay, so then this u would be given by 2u sin theta, right? So if we just substitute this, we will get 1 minus u square by capital U square, 2u sin theta whole square by u square, right? 1 minus 4 capital U square sin square theta by u square. This u square will get cancelled. Okay, then we get 1 minus 4 sin square theta. Okay, so we have to find the location at which our coefficient of pressure becomes 0, right? So then we will equate this 1 minus 4 sin square to get the angle at which it becomes 0. So 4 sin square theta is equal to 0. Then the sin square theta is equal to 1 by 4, and then which gives sin theta will become 1 by 2 plus or minus 1 by 2. So now we have 4 quadrants, right? So at 4 different locations we will have a plus or minus, at here we will have a plus half at 30 degree, right? At 150 degree, sorry, 150 degree, so we will get minus half, right? So similarly at 4 different coordinates we will have different angles, but in this question we have been asked to find the angle at which it becomes 0 in the first quadrant, right? In the first quadrant at which the sin theta becomes 1 by 2 is 30 degree, right? So the azimuthal location would be 30 degrees. So let's go back to the question. So the azimuthal location on the cylinder at which the pressure coefficient becomes 0 is 30 degrees, right? So if you want to know more about the similar concepts, you can refer to the NPTEL course Fundamentals of Theoretical and Experimental Aerodynamics by Professor Arnav Roy from IIT Kharagpur. You can also refer to the lecture number 22 in which the flow over cylinder is explained, which is elementary flows, doublet and point vortex, and the vortex sheet. You can also see the YouTube link for the particular lecture here. So that's all for this question. Thank you.